All right, so let's just talk very briefly about why it is that free energy is what determines spontaneity and not this enthalpy here, not what the change in enthalpy is. And it really comes in terms of remembering it in terms of the definition. When we think about delta G, what that is that it's energy that's released or used in the reaction, but if it is released, that it can directly be used to do work. It's what we call free energy. It's free to do other things. Whereas when we were talking about enthalpy here, well, this is the amount of heat that's released when we break and form the bonds in the reaction, but some of it actually gets stuck in the molecules, and this is just a way to think about it. That this term here is one way we can think about it as just some energy that's getting stuck. So for example, molecules, which we don't really go into in this class, have vibrational movements, they have rotational movements, there's energy associated with that can sort of get stuck, as we could say, some of the enthalpy that's released in terms of forming and breaking the bonds in our reaction. So that's a case where we could see that we have a negative delta H, but we still end up with a positive delta G. And again, I haven't really gone into what entropy is here yet, and we will just in a few minutes. But first, I want to take a look at one of the examples that we talked about, which is the conversion of ammonium nitrate when it's solvated, breaking up into its ions. So what I had told you is that, in fact, this is a positive delta H, but still that the reaction is spontaneous. So let's just do this calculation and see if we can confirm that in terms of delta G. So the reaction, again, that we're going to use is delta G equals delta H minus T delta S. So if we're talking about room temperature here, ooh, that's a bad piece of chalk. So we're going to say that delta G, in this case, is going to be equal to 28 kilojoules per mole minus, we're at room temperature, 298 Kelvin. In this reaction, you always put temperature into Kelvin. And then we need to multiply it by the entropy, which is 109 joules per Kelvin mole. I want to point out that entropy tends to be a much smaller value than enthalpy, so it's reported in joules instead of kilojoules. When you solve these problems, it's really important to convert it into kilojoules so that your units work out and you don't get a completely crazy answer. So we want to convert this to 0.109 kilojoules per Kelvin mole. So we can just rewrite this. So we have 28 kilojoules per mole. Then this term here will be 32.5 kilojoules per mole. So what we end up with, our delta G for this reaction, is going to be negative 4 kilojoules per mole. All right, so talking about this as a negative delta G, would you say this is a spontaneous or a non-spontaneous reaction? Yeah, it's spontaneous. So what we're going to see is delta G negative 4. So this reaction is spontaneous even though our enthalpy change was positive.